Fick's law of partial pressure, and it states that the pressure of a gas mixture is the sum of the partial pressures of the individual components of the gas mixture. P nitrogen is the partial pressure of the nitrogen, and P oxygen is the partial pressure of oxygen. P nitrogen equals N nitrogen RT divided by V. P oxygen equals N oxygen RT divided by V. You will notice that the equations for the partial pressures are really just the ideal gas law, but the moles of the individual component, nitrogen or oxygen, are used instead of the total moles. Conceptually, P nitrogen is the contribution nitrogen molecules make to the pressure, and P oxygen is the contribution oxygen molecules make. Here is another example. We have 2 moles of H2, 4 moles of O2, and 6 moles of He in a 5-liter vessel at 27 degrees centigrade. How do we determine the partial pressure of each gas and the total pressure of the mixture? Step 1. Convert the temperature to Kelvin. Step 2. Next, using the ideal gas equation, that is PV equals nRT, determine partial pressure for H2, O2, and He. Step 3. Then add all the 3 partial pressures to get the total pressure. In this example, the total pressure is 59.05 atm. Avogadros Law states that under conditions of constant pressure P and absolute temperature T, there is a direct relationship between volume V and number of moles N for an ideal gas. Mathematically, Avogadros Law can be represented as follows. In 1829, Thomas Graham used an apparatus similar to the one shown here to study the diffusion of gases, the rate at which 2 gases mix. This apparatus consists of a glass tube sealed at one end with plaster that has holes large enough to allow a gas to enter or leave the tube. When the tube is filled with H2 gas, the level of water in the tube slowly rises because the H2 molecules inside the tube escape through the holes in the plaster more rapidly than the molecules in air can enter the tube. By studying the rate at which the water level in this apparatus changed, Graham was able to obtain data on the rate at which different gases mixed with air. Graham found that the rates at which gases diffuse is inversely proportional to the square root of their densities. That is, rate diffusion alpha 1 divided by the square root of density. This relationship is eventually known as Graham's law of diffusion. To understand the importance of this discovery, we have to remember that equal volumes of different gases contain the same number of particles. As a result, the number of moles of gas per liter at a given temperature and pressure is constant, which means that the density of a gas is directly proportional to its molecular weight. Graham's law of diffusion can therefore also be written as follows. Rate diffusion alpha 1 divided by the square root of mw. Mathematically, the Graham's law can be written as follows. In the real world, all gases fail to obey the ideal gas law. This can be illustrated by plotting the experimentally determined value of PV divided by RT for exactly 1 mole of various real gases as a function of pressure P. The graph shows a deviation from ideality. The variable PV divided by nRT equals Z is called the compressibility factor. The value of Z is unity for an ideal gas. The deviation from ideal behavior is large at high pressure and low temperature. At lower pressure and high temperature, the deviation from ideal behavior is typically small. In this case, the ideal gas law can be used to predict behavior of the gases with little error. Let's look at the example of the deviation from the ideal behavior for a nitrogen gas as a function of temperature. Do you remember the conditions assumed for an ideal gas? In an ideal gas, molecules are assumed to be perfectly elastic, no stickiness. The molecules are also presumed as point masses, no size, and they move at random motion. The first two of these assumptions is clearly false for all gases, because at low temperatures all gases condense or they form a liquid. This phenomenon happens because the molecules stick to one another. At high pressure, the intermolecular distances can become quite short, and attractive forces between molecules become significant. Neighboring molecules exert a relatively long-range attractive force on one another, which will reduce the momentum in which they transfer to the container walls. The observed pressure exerted by the gas under these conditions will be less than that for an ideal gas. One of the most useful equations to predict the behavior of real gases was developed by Johannes van der Waals. It takes into account the molecular stickiness and molecular size. Unlike the universal gas constant R, the van der Waals constants A and B are different for different gases. For an ideal gas, this temperature and volume would lead to conditions of standard temperature and pressure, or STP, that is, a pressure of exactly 1.0 atm.